Very good morning, students. In yesterday's class, up to Kolb's reaction we have completed, and we will continue the topic. That is, in today's class, we will go through Riemann-Tiemann reaction. This Riemann-Tiemann reaction is involved with conversion of phenol to salicylaldehyde, in which first step, phenol reacts with NaOH. Phenol reacts with NaOH. We will get sodium phenoxide. This OH present here and hydrogen present here will be removed as water. We will get sodium phenoxide. In second step, this sodium phenoxide reacts with chloroform, in which in ortho position of sodium phenoxide Na. The sodium phenoxide, in which in ortho position we have hydrogen, and here CHCl3 we have 3 chlorine atoms, in which one chlorine present here and hydrogen present here will be removed as HCl to get ONA, and in ortho position CHCl2. Here in ortho position we have hydrogen and the chlorine will be removed as HCl, and the CHCl2, this carbon is going to be bonded to this ortho position and it will form this one. Now, the sodium phenoxide with the CHCl2 will be hydrolyzed in presence of NaOH. We will get salicylaldehyde. Conversion of this phenol, actually here in presence of hydrolysis, this one here itself, this ONA also will be converted to OH, okay, and the CHCl2 is converted to CHO. How this CHCl2 is converted to CHO, I will explain. Before that, conversion of this phenol to salicylaldehyde. Is called Riemann-Tiemann reaction. Named reactions, these are, every named reaction is very important in your revision part, okay, for your exams. And this whole reaction is called Riemann-Tiemann reaction. Now, how this part is converted to CHO, that one we will see. Before that, as it is, you can note down now how this step alone, how this CHCl2 is converted to CHO, we will see now. The sodium phenoxide with CHCl, it is going to be hydrolyzed in presence of NaOH. Okay, now that NaOH, actually in presence of NaOH, water will give OH minus ions as well as H plus ions. In presence of that NaOH, water will give H plus ions and OH minus ions. Here, correctly, these two chlorines in the form of Cl minus and in the form of Cl minus, they will be reacted with this H plus and H plus to form HCl, 2 moles of HCl. So instead of these two chlorines, exactly we will get these 2 OH minus ions. Then we will get the substance, that is CHOH. This is the substance we will get. But we know, actually this ONA is also there, no? We know on same carbon with two OH groups, the carbon will not be stable at all. Then what will be happened? From this hydrogen and this OH will be evolved as H2O, and we will get double bond here. Then finally resulted compound is ONA. Here we will get double bond CH double bond O, which is called aldehyde. And this ONA can be converted to alcohol easily. That is not a problem at all. Now this is converted to CHO. So how this CHCl2 is converted to CHO? For you, explanation I gave. No need to note down. Actually, if you want to note down, right side, make a margin and note down there. In fair notes, whole reaction itself it is enough. Is it okay, ma'am? So what is the reagent in Riemann-Tiemann reaction? Chloroform and NaOH. What is the reagent in Riemann-Tiemann reaction? Chloroform and NaOH. When phenol reacts with chloroform in presence of NaOH, that phenol will be converted to salicylaldehyde. Other name of this salicylaldehyde is orthohydroxybenzaldehyde. Actually, IUPAC name is 2-hydroxybenzaldehyde. Commonly it is called salicylaldehyde. This whole conversion of phenol to salicylaldehyde is called Riemann-Tiemann reaction. Okay, ma? This is about the named reaction. Next, after completion of this, we will go through reduction, how phenols will undergo reduction. Okay, now this phenol will undergo reaction with zinc dust. This phenol will undergo reaction with zinc dust. This is very important reaction in the conversion of phenol to benzene. Understand carefully. This zinc and this O, correctly this O and this zinc will be combined as ZnO. This hydrogen is going to be reacted with this one to be formed as benzene ring. Removal of oxygen is happened. Removal of oxygen is also called as reduction. And phenol will undergo reduction with zinc dust. We will get benzene plus ZnO. Benzene plus ZnO. Next reaction is oxidation. Actually, this is second reactions. Under reactions of phenol, we have started with electrophilic substitution reactions. Up to that named reactions, all are treated as electrophilic substitution reactions. Second one, reduction reaction. Third one, oxidation reaction. Under this oxidation reaction, this phenol will undergo oxidation in presence of strong oxidizing agent, that is Na2Cr2O7. Phenol will undergo oxidation in presence of strong oxidizing agent, that is Na2Cr2O7. We will get this alcohol is converted to double bond O, as well as in para position also we will get double bond O. And this double bonds adjustment we have to see. Benzene ring will be collapsed. 3 double bonds are there, but here only 2 double bonds are there. This is called benzoquinone. And these are the two continuous reactions for phenols. First one is phenol will undergo reaction with zinc to form benzene plus ZnO. This reaction is called reduction reaction. Under this oxidation, phenol will react with powerful oxidizing agent, that is Na2Cr2O7, to get benzoquinone as the substance. And these are the reactions of phenols. After this reactions of phenols, we have some commercially important alcohols. Those two are methanol and ethanol. That methanol and ethanol, that is commercially important alcohols. In the last we will go through. Now immediately we will start with ethers. Till this correctly, we completed alcohols and phenols. Actually, one small topic is there. Good morning, students. After completion of the alcohols and phenols, we will go through ethers. Under ethers, first thing we will go through, that is classification of ethers. Just 1 second, man. Okay, under this classification, we can classify these ethers into two types. Those are symmetrical ethers and unsymmetrical ethers. Which are called symmetrical ethers and which are called unsymmetrical ethers. We know what is the general formula of, what is the molecular formula of, general formula of ethers. ROR, in which two alkyl groups are going to substitute two hydrogens present in water. Water formula HOH. The two hydrogens are substituted by two alkyl groups, then it is called ether. Okay, now this ether in which, when it is called symmetrical ether, if you have two alkyl groups which are bonded to oxygen, those are same. Two alkyl groups which are bonded to oxygen, those are same. That is called symmetrical ether. The two alkyl groups which are bonded to oxygen are not same. That is called unsymmetrical ether. Symmetrical ethers are represented with ROR. Unsymmetrical ethers are represented with ROR dash. To differentiate R and R dash, that is one thing, it is represented with R dash 1. And this is about classification of ethers. Ethers are classified depending on the type of alkyl groups attached with oxygen. These are two, symmetrical and unsymmetrical ethers. CH3OCH3, C2H5O C2H5. These are all examples for symmetrical ethers. And coming to unsymmetrical ethers, CH3OC2H5, C2H5OC3H7. These are all coming under unsymmetrical ethers. Okay. After completion of this classification, we will go through nomenclature of ethers. Nomenclature is nothing but naming of ethers. Let us consider first symmetrical ether. Symmetrical ether in which both alkyl groups are same. Now let us consider CH3OCH3. When we have two alkyl groups same, then what we will do? Select any one alkyl group, because both have same number of carbon atoms, no problem. So select any one alkyl group and join with this oxygen. This combination is generally called alkoxy. This combination is generally called alkoxy because this is alkyl group and this is oxygen. Alkyl group and oxygen, it is called alkoxy. Okay, next, as we have particularly one carbon methyl group, this is called methoxy. This is called methoxy. After giving the name of this combination of oxygen and alkyl group, that is called alkoxy, remaining carbon chain contains how many carbons? Here remaining carbon chain has one carbon. Remaining carbon chain with one carbon is called methane. Here no double bonds are present, all are single bonds. So this is methane with substituent methoxy. This one treated as, actually methane formula CH4, methane formula CH4. Instead of this hydrogen we have methoxy. Like that it is treated and it is given name as methoxy methane. What is the name of this compound? Methoxymethane. So if you have symmetrical ether, that symmetrical ether contains two alkyl groups bonded to oxygen are same. So first step, we have to select any one alkyl group and it should be combined with oxygen. and it is commonly called as alkoxy, generally called as alkoxy. Okay, under this alkoxy, if we have one carbon, that is called methoxy. If we have two carbons, that is called ethoxy. If we have three carbons, that is called propoxy. Like that, we will give names. So this one is joined with this oxygen and we will call it as methoxy. Remaining carbon chain contains how many carbons? One carbon. So this is called methane, and methoxy methane. This is the complete name of this ether. So when we have symmetrical ether, this is the procedure. Join any one alkyl group with oxygen and it is called alkoxy, and the remaining carbon chain contains how many carbons? According to that, we will complete with this alkane. This is treated as methane. Okay, this is how we will give name for symmetrical ether. Next, what about unsymmetrical ether? If you have unsymmetrical ether, unsymmetrical ether means the two alkyl groups which are bonded to oxygen are not same. Then let us consider CH3O C2H5. CH3O C2H5. These two alkyl groups are not contained by same number of carbon atoms. Then what we are going to do? Out of these two, select the alkyl group with less number of carbons and join with oxygen. Select the alkyl group with less number of carbons and join with oxygen. Then this is generally called as alkoxy. Now we have how many carbons? One carbon joined with oxygen. Then it is methoxy. Remaining how many carbons we have? We have two carbons. Carbon chain with two carbons, root word eth. All are single bonds only, no double bonds are present, ethane. So this is called methoxyethane. Methoxyethane. Like this, if we have one more unsymmetrical ether, let us consider C2H5O C3H7. Like this, they give one unsymmetrical ether. Now in this one, what is going to happen? Out of these two, which alkyl group has less number of carbons? This one. Then that is joined with oxygen, and this is called ethoxy. Because this alkyl group has two carbons, that is ethoxy. Remaining out of the chain means this parent chain contains how many carbon atoms? 3 carbon atoms. Root word for 3 carbon atoms carbon compound is prop. So the name will become ethoxypropane. Ethoxypropane. And this is how we are going to give the name for unsymmetrical ether. Is it okay, ma'am? Now, unsymmetrical ethers we will select in which out of two alkyl groups, we have to select the alkyl group with less number of carbon atoms and it must be joined with oxygen. Okay, and it is given as alkoxy. After that, select that carbon present in that alkoxy group. Now it has one carbon, so it is methoxy. Remaining carbons, that is chained with ethane. Methoxyethane, ethoxypropane. Like that we will continue with names. In the same way, we can give name for aromatic ethers also. Let us consider one example for aromatic ether. That is aromatic means aryl group and alkyl groups are bonded to oxygen. That is aromatic ether in which alkyl group with less number of carbons, this one, this is joined with oxygen, and that group is called methoxy. And that group is called methoxy. And the remaining thing is called benzene ring. So methoxy benzene. The name of the compound is methoxybenzene, and it is generally called as anisole. And this is how we can give the names for ethers. You can go through the table column given in your textbook. After going through that one, if you have any doubts, we will just discuss, no problem. Through WhatsApp you can send to me and I will just clarify that doubt and I will send to you. Okay, na? This is about nomenclature. After completion of the nomenclature, we can go through the preparations of ethers. We have two preparations of ethers now. Under preparations, first preparation is intermolecular dehydration of alcohols. Intermolecular dehydration of alcohols. What is meant by dehydration? Dehydration is the process of removal of water. Dehydration is the process of removal of water. Inter means between. Intra means in the molecule itself. Inter means between. Intra means in the molecule itself. Intermolecular. Between the molecules, we will remove water for alcohols. Then we will get ethers. When we remove water molecule from alcohols, in that way, two alcohols will be combined. By the removal of water, we will get ether. That is the meaning of this intermolecular dehydration. Now, how it will undergo intermolecular dehydration, we will see. Just 2 minutes more. Okay, now let us see in what way this dehydration is going to be happening. Let us consider one alcohol, ethyl alcohol, CH3, CH2OH. The CH3, CH2OH will undergo reaction with H2SO4 at 413 Kelvin. This temperature is very important here. CH3CH2OH reacts with H2SO4. Concentrated H2SO4 is a dehydrating agent, means it will remove the water. At what temperature? 413 Kelvin. We will get CH3CH2O CH2CH3, which is ether. Same alcohol, if it undergoes reaction with concentrated H2SO4 at 443 Kelvin, higher temperature, elevated temperature. Okay, at 443 Kelvin, in which this one will undergo intramolecular dehydration. Intramolecular means in the molecule itself. It will be formed as CH2 double bond CH2. If alcohol undergoes intramolecular dehydration, we will get alkene. If alcohol undergoes intramolecular dehydration, we will get alkene. If alcohol undergoes intermolecular dehydration, we will get ethers. This process is called intramolecular dehydration and this process is called intermolecular dehydration. When it is undergoing intermolecular dehydration, 2 moles of alcohol will be involved to be formed as ether. When it undergoes intramolecular dehydration, intra means in the molecule itself, no need of 2 moles, only 1 mole will undergo reaction in which from one carbon OH will be removed and from another carbon hydrogen will be removed, we will get alkene. Okay, actually this is in this way we will represent it, but we will discuss the mechanism of this reaction also. How we are going to get ether also, we will discuss the mechanism. Shall we see the mechanism? Okay, now let us go to the mechanism. This is Now we are discussing intermolecular dehydration. Means how many moles of alcohol must be required? 2 moles. Then we will take first mole, that is CH3 CH2 OH. Oxygen has 2 lone pairs. Okay. Now it is going to react with H plus ion. This H plus ion is generated from H2SO4 is dissolved in water. When H2SO4 dissolved in water, it will furnish H plus ions. That H plus ion is going to react with this alcohol in a way that one of the lone pairs present in oxygen will be donated to H plus. Okay, to be formed as CH3 CH2 O plus. If it donates lone pair, oxygen will get plus charge H and H. This step is called protonation of alcohol. This step is called protonation of alcohol. Next, second one. This protonation of alcohol, after having this one, CH3 CH2 O plus lone pair H and H. This is going to be attacked with first step, CH3CH2OH is going to attack this H plus, in which this lone pair of electrons is going to attack this H plus to be formed as CH3CH2O plus and HH here. Okay. Now next step, this is going to be attacked with one more mole of alcohol. This one is going to attack with one more mole of alcohol, in which this lone pair of oxygen is going to donate to this carbon. This lone pair of electron of present on oxygen is going to donate to this carbon. At that time, this carbon-oxygen bond is cleaved to O. We will get this positive charge neutralized to get water. So this is resulted as CH3 CH2 O. After donation of this lone pair, this oxygen will get positive with one lone pair already present. H is there. Now this oxygen is going to form bond with this carbon, continuation CH2 CH3. This oxygen is going to form bond with this carbon, in which we will get this compound totally. Okay, now oxygen with positive charge is not at all stable, in which this OH bond will be cleaved towards oxygen side. OH bond is cleaved towards oxygen side. Finally, you will get the substance CH3 CH2 O with two lone pairs of electrons, CH2 CH3. This is ether. Plus H plus is removed. This is H plus. Initially we used this H plus and finally we got this H plus. Again this H plus is going to be reacted with one more mole. In the same way reaction is going to be continued and finally we will get ether with H plus. That's why H plus acid, it is acting like a catalyst. This is called acid catalyzed dehydration. Even this is also called acid catalyzed dehydration, because acid is involved in the reaction. Finally it is again coming out. Okay, it is acting like a catalyst. This is about mechanism of formation of ether. This total mechanism is involved with 2 moles of alcohol. In between these 2 alcohols, we have removed water molecule. Here water molecule is removed plus H2O. Dehydration is happened between the molecules. This is called intermolecular dehydration. This is called intermolecular dehydration, and finally we got this ether. Okay, this is about first preparation, that is intermolecular dehydration of alcohols. Next, we will go through next preparation, that is called Williamson synthesis. equation na Williamson synthesis. Williamson synthesis is generally represented with RONA, which is called sodium alkoxide. RONA, which is called sodium alkoxide, is going to react with RX. RX is nothing but alkyl halide. RX is nothing but alkyl halide, in which when these two are going to react in a way that this RO minus and this is Na plus, in between R and X, R is getting negative charge, positive charge, no? X is getting negative charge because X is more electronegative than R. Okay, we will get R plus and X minus. Now, exchange of cations and anions will be happen. Actually, this is not an ionic reaction. While the bond is getting cleaved, heterolytic cleavage will be happen and we will get discharge. But it will be a slow reaction. Okay, now this RO minus and this R plus will be combined as ROR plus NaX, which is called ether. This is called Williamson synthesis. RONA plus RX reacts with this one. Both are going to be reacted to form ether plus NaX. This is called Williamson synthesis. But we have an application in Williamson synthesis now. That one we have to see. If you want to obtain an ether like CH3O, CH3, CH3, CH3. We want to obtain this ether. Okay, to obtain this ether, what are the reactants we have to take? That is important here. Now let us see that one. This is application of Williamson synthesis now. Okay, now to obtain this ether, what we are going to take? First one, CH3Cl, alkyl halide, is going to react with sodium alkoxide, CH3, 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 O, Na. Like this we can take. When we take like this is O minus and this is Na plus. Here this is CH3 plus and this is Cl minus. Okay, this O minus will attack this CH3 plus and remaining Na plus and Cl minus will be combined to form this substance. It is correct procedure. But if you take CH3, 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 Cl plus CH3O, Na plus O minus. If you take, see, this is CH3Cl. Now we are taking CH3ONA. I took reverse. This alkyl group is like alkyl halide I took. Tertiary butox. Here tertiary butoxide, sodium tertiary butoxide. Here tertiary butyl chloride. Tertiary butyl chloride. Okay, find the difference, please. Here we have taken primary alkyl halide. Here we have taken tertiary alkyl halide. And this is small nucleophile. Here this is bulkier nucleophile. Okay, now this one is going to attack this CH3 because this is less hindered. Means it is less crowded. Because of that, according to our expectation itself, it will undergo reaction to form this product. No problem. But if you take like this, what is going to be happen? Here this is the nucleophile. Previously this is nucleophile, this entire thing. Now this is the nucleophile in which it cannot attack this central carbon. It cannot attack this central carbon because chlorine contains lone pair of electrons which is bulkier. These methyl groups are also bulkier, in which this carbon is present between all the bulky groups, in which the nucleophile cannot be attacked this central carbon. This nucleophile cannot attack this central carbon because highly sterically hindered. This is sterically hindered big group, this one also. Because of this more space, and chlorine also contains 3 lone pairs, this CH3O minus cannot attack this carbon, so it is not possible. Then what will be happen? Instead of attacking this central carbon, this CH3O minus will attack this hydrogen. And this bond is there now. It is shifted as double bond, and this chlorine will be left out. You will get the product CH3C, CH3. Here you will get double bond 1, double bond CH2. We will not get ether. We will get alkene. When we take bulkier alkyl halide and this one. So preferably, if you want to prepare ether, preferably we have to take primary or secondary alkyl halides. Other thing will be in the form of alkoxide. Understood, ma? This is the difference between two reactions. Here we have taken one way and another way. In this way, our given product will be formed. In this way, we will not get the given product, that is required product, that is ether. We will get alkene. So separately write these two reactions. This is one reaction to form this one, and this one will undergo reaction to form alkene. Okay, this is about Williamson's synthesis. By this we completed preparations of ethers. Next we will continue with chemical properties of ethers and physical properties in the next class. Okay, thank you, ma'am. Thank you all.